can speak out what is the value of zeta? Yes, it comes out to be 0.46. Anyone getting this? And now the peak time is given to be 2 seconds, right? So the expression for the peak time, that is pi upon omega n root over 1 minus zeta square. Okay, right? Now from here, this expression and this expression we have to use. Once we have got the value of zeta, what we can find out? Omega
Omega.
n, right? So substitute the values. 2 equals pi divided by omega n 1 minus 0.46 square. So omega n comes out to be how much? Be ready with your calculators and calculate quickly and tell me the values what you're getting. Yes, how much?
1.35 or something.
1 point
4.
omega n
Around 4.
1.35,
35.
right? So omega n square will be 1.35 square, right? And once you got the value of k, we can from this expression compute our t. Okay, so find out this. And t comes out to be 2 into 0.46 into 1.35 divided by k. How much is k? Square of this?
1.8.
The square of 1.35 is 1 point.
4.
1.82.
1.82, right? So how much is the value of t? Yes.
Mm, 2.
0.68.
You're getting it as
2, I think.
2 seconds.
Yeah.
You have to evaluate it again. I guess your answer is not correct.
0.7 seconds.
See what you're getting? Exactly, you're getting 2?
No, ma'am. I think I have made one blunder.
Yes, yes,
0.5.
right. 0.5. Okay, right?
Yes, sir.
So I'm giving a similar type of question here again with slight change. Let us see that. Uh, Open loop transfer function of a unity feedback system is given by Gs equals K by S1 plus St. Now, the problem is that by what factor K should be multiplied. So the damping ratio is increased from 0.2 to 0.8. Okay. We want an increase in damping ratio from 0.2 to 0.8. And by what factor? T should be multiplied so that the damping ratio is reduced from 0.6 to 0.3. Here we want an increase. Okay. And here we want a reduction. Okay. So we have to calculate the values of K and T for this. Right? First case, we have to find out K. Second case, we have to find out T. Right? And here the value of HS is 1. Right? So we can find out the transfer function for the system. We can start it like this. Okay. So if we find out the transfer function CS by RS, that is GS by 1 plus GSHS, K by SST plus 1 divided by 1 plus K SST plus 1, it comes out to be K S square plus S square T will be there, right? S square T plus S plus K. Okay, right? Can I rewrite this as K by T S square plus S by T plus K by T? Okay.
Yes,
Now I can compare this transfer function with the standard form, that is omega n square S square plus 2 zeta omega ns plus omega n square. So on comparing with standard form, what I'll get? Omega n square will be K by T, right? Or I can write down that omega n is root over K by T. And 2 zeta omega n is 1 by T. Right? Okay. So from here, can I write down zeta equals 1 by 2 omega nt? Right? And now we have a value of omega n as root over K by T. Can I substitute it here in this expression? Okay. So what it will become? 2 root over K by T into T square, right? If I can write down this T as T square here. So I'll get here 1 by 2 root over KT. Fine. Is it
yes, sir.
okay up till here? Now see, my condition is that what factor should be multiplied with K, and so that the damping ratio is increased from 0.2 to 0.8. Can I write down this as, now for part A, my zeta 1 is 0.2 and I'm writing it as 1 by 2 root over K1 T1. Okay, for the value of zeta is 0.2 and zeta 2 equals 0.8, 1 by 2 root over K2 T2. Correct? Fine.
Yes, ma'am.
And what we'll do here, our this T is going to be equal. Okay. Only the zeta has to be, zeta is like the values are changing. So I can write down here that T1 is equal to T2. So if I take the ratio of zeta 1 by zeta 2, that is 0.2 by 0.8, what it will become? it will become as ratio of root over by K2 by ratio of K2 by K1, right? So now we will have a relationship between K2 and K1. Find it out what it comes out to be, or squaring both the sides, see what you're getting. K2 by K1 is equal to, you can write down this as 1 by 4 square, or that is 0.25 square, that is 0.0625, right? Or your K2 is 0.0625 K1. Okay, so the gain K is reduced by a factor of, you can see here, of 0.0625 if we want an increase in the damping ratio. Is it okay? Clear?
Yes, ma'am.
So we go to the next part. Okay, so in the second part, your damping ratio is reduced from 0.6 to 0.3, right? So I can, again from the same expression, I can write down this as 0.6 by 0.3 equals, see here, here we have considered that T1 is equal to T2, right? And here in the second case, we have to see that by what factor T has to be multiplied, right? In the question, what factor T has to be multiplied. So in this case, our K1 will be equal to K2. Do you get it? Yes?
Yes, ma'am.
That
Yes.
is not mentioned exactly in the problem, but we have to assume that, right? So what will our expression now be from here? It will be root over T2 by T1 as K1 is equal to K2, right? So how much you're going to get? This will be 2. So T2 by T1 is 2 square, and on solving this, what you'll get? T2 is equal to 4T1. So T2 must be increased, you can say, 4 times to reduce zeta to 0.3. Do you get it?
Yes, ma'am.
Okay. So now let us see a problem based on the Bode. Okay. Bode plots we have seen. So let us see how to solve this problem just analytically without using the graph. We have a unity feedback system, okay, that is given to us, and this is the system whose transfer function, this k e to the power minus s by s. The input is rs, output is cs, and this is a unity feedback system. So what has to be computed here is what will be the value of k, okay, that results in a phase margin of the system to be 30°, right? We have to find out that value of k here. Is the question clear?
Yes, ma'am.
Okay. So let us see how we'll do this problem. So you know that the phase margin, Okay, you tell me what is GS here? That is K e to the power minus S by S. Fine. So,
Yes.
yeah. What is a, how can we write down the phase margin of the system? That can be written as, yes.
Angle of this.
Hmm?
Is it the angle of this?
Yeah.
Angle of the system at gain
Minus
cross
90 degree.
over frequency.
Hmm?
Angle of the system at gain cross over
Angle
frequency.
that will find out the angle. But what is the expression for the phase margin? That is 180
180
degree
plus
plus angle of,
GS.
yes. This we have already discussed, right? And this GC represents our gain crossover frequency, right? If we see the
Yes.
magnitude of at the gain crossover frequency, I can write down this as the magnitude of the function, the gain, sorry, that is at GC, that is equal to 1, right?
Yes.
Yes. So now for the system that is given to us, this should be equal to 1, right? Of course, when we are putting the value of S as j omega, right? So this is K e raised to power, sorry, this is minus S, minus j omega at the gain crossover frequency by j omega at the gain crossover frequency should be equal to 1. Now tell me, if I evaluate this expression, what I'll get? Yes,
K by omega GC equals 1.
right? All of you. This e to the power minus j omega gc, the magnitude of this is going to be 1 because this is a rotation on a unit circle in complex plane, right? So its magnitude is going to be 1. So the magnitude of k will be k. And again, if we find the magnitude of this, it will be omega gc, right? So this is equal to 1. So can I write down this, that omega gc, that is the frequency at the gain crossover, that is equal to k. Fine. Okay.
Yes.
Now, if I want to find out the phase of my this transfer function or phase of this uh, GS, what it will be? I've just seen the magnitude, right? Can I write down this as angle of j omega, that is angle of what it is, k e raised to minus j omega divided by j omega, right? Fine.
Yes.
Now, what will be the angle that I have to find out, right? So, this pole at j omega, that is contributing an angle of 90 degree, right? So, I can write down this, this is a constant. I can write down this as e to the power minus j omega, and this is contributing an angle 90, so it becomes minus 90, right? What about this factor? How much angle it is going to contribute? Yes,
Omega.
that is angle e to the power minus j omega, that is minus omega. Fine. This is in radians. Okay.
Mm,
It is minus omega, not omega. right?
Yeah, yes.
Right? So this is in radians. Now I have to change it in what? Degrees.
Degree.
So what I'll do, I'll multiply this by 180 by pi, right? Because here this is in degrees. So what it will become? Minus omega into 180 by pi minus 90. Is it correct? Do you get this step? Okay.
Yes, ma'am.
So of course this is at your gain crossover frequency, right? Okay.
Yes, ma'am.
So now we can solve it easily because our phase margin expression is known to us and we have evaluated this angle, right? And our phase margin has to be 30 degree. So putting the values, I can here phase margin is equal to 180 degree at an angle for this gain crossover frequency. This should be 30. This is 180 plus this is minus omega GC into 180 by pi minus 90. Right? Okay. So how much it will give you? Now at this value of this omega, okay, that at that value we have to evaluate K. Okay. So can I write down this as 30 is equal to 180 minus 90 from here, this, right? We have already seen that this is equal to K. Fine. So can
Yes.
I write down here as this is minus 90 plus this is minus K into 180 by pi, right? So tell me what is the value of K? Find it out quickly.
60.
Yeah, that is pi by 3, right?
Yes.
K comes out to be 60
60 degree, my
degree, right? And on changing it into radians, how much you'll get?
pi by 3. Around 1 point something, I think.
Yes, yes, correct. 1.04 something you'll get, okay? So is
Yes.
this question clear to you? If this type of questions come, you'll be able to solve it, right? 1.04. So I'm giving you one more question. Similar type. You just try it and see. You have to find out the value of A where the open loop transfer function of the system is given as GS is equal to 1 by S AS plus 1. And this value of A should result in a phase margin of 30 degree. Right? So for this value of A, my system should have a phase margin of 30 degree. So how I'll proceed for this problem? Tell me the steps. Yeah, you've just seen.
Should we find mod of G?
Yeah, correct. We'll find out the magnitude
Then the
at the gain crossover frequency. Then we'll find out, of course, the angle. And then we can find out the value of A from both the expressions. Okay. You just give it a trial. I'm giving you 2 minutes for it. Okay. What is the magnitude you're getting? At the gain crossover frequency. How much that is? G of j omega, and its magnitude should be equal to 1, right? So what is g of j omega? What you people have got? 1 by j omega a j omega plus 1, right?
Yes.
Correct? So if you find out its magnitude, how much it comes out to be? Yes. 1 upon yes, tell me.
to raise to omega power to plus omega
1
square.
upon omega square. This is omega, right? Not omega square. Then root
Root
over
over a omega square.
1 plus a square omega square, right? And this is equal to 1.
Yeah.
Fine. So on squaring both sides, can I write down this as 1 equals omega square 1 plus a square omega square? Can I write it like this?
Yes, ma'am.
Are you getting it?
Yes, ma'am.
Okay. Now, the phase margin is given as 180 degree plus angle of G at gain crossover frequency, right? Fine. And this is given to be 30 degree. So can we here find out what is the angle? Tell me how much you have evaluated.
-1.
See, this is a pole here, right? So it is going to contribute 90 degree. So I can write down this as minus 90 degree, right? And this is going to contribute an angle of tan inverse A omega. Okay. So this can be written as minus tan inverse of A omega. Correct? Now, can I substitute it here? This will become 180 plus minus 90 minus tan inverse of A omega, of course, at this frequency, at and this is equal to 30, right? So if you solve it, what you will get for tan inverse A omega at gain crossover frequency, how much you are going to get it?
60 degree.
60.
60. Okay. Both the sides of a negative sign, 60. So A omega GC, that is tan 60. And what is the value of tan 60? Yes, root 3. Correct. Okay. So we have this as value of A omega as root 3. So see here, this equation number 1, I can substitute here 3 and I can calculate the value of omega, right? So from 1, omega square 1 plus 3 is equal to 1. So omega square will be 1 by 4, or omega is equal to 1 by
1 by
2, and this is 0.5, right? So now can we get the value of A from here? Yes, A will come out to be root 3 divided by 0.5, or you can write down this as 2 root 3, or this is 2 into 1.732, right? So is this clear?
yes, ma'am.
You want more problems on this, how to solve the questions on Bode using analytical methods, or this is sufficient now? I guess you got this, right?
Yes, ma'am.
Okay, someone raise hand. Subhash, you can just speak out, because now presenting the screen and then like looking at what you people are writing is not possible.
Am I audible now? Hello.
Yes, yes, you're audible. Yes.
So yeah, no, this is fine. Like I'm having a query. So can you explain a few questions
Hmm.
about converting from one canonical form to other canonical forms in state
You
space?
can be a bit louder, please. Please repeat again.
A question about uh, how to convert from one canonical form to other canonical form in state space.
Canonical conversion.
Yeah, exactly.
Yeah, we'll see that also.
Yes.
We'll see that. I'll tell you that thing. In one of the lectures I've explained, I guess in the last lecture we have taken that topic. But if you have doubt, we'll discuss it again. Okay.
Sure, ma'am.
Okay, I'm giving you one more question. You can just give it a try yourself. Okay. You can just note it down. Uh, the open loop transfer function for the unity feedback system is given as GS is equal to K upon S plus 2, S plus 20. Okay. So you have to find out the value of K for phase margin of 50 degree, and that too analytically without going for the plot. Fine. You try it. K will come out to be 171.49, right? You solve it. Okay. Fine.
Yes, ma'am.
Yes, ma'am.
Okay. So let us do one question based on this stability. Okay. Uh, here, for a unity feedback control system, the open loop transfer function GS is given as K by S plus 2, S plus 4 by S square plus 6, S plus 25. Okay. Now you have to discuss the stability of this closed loop system as a function of K, right? You have to discuss the question is you have to discuss the stability of the system as a function of K, and also you have to determine the value of K which will cause sustained oscillations in the closed loop system. Got my point? What do you have to do?
Yes, ma'am.
Okay. So how will you proceed? Tell me the steps.
Should we find the poles first or?
Poles. You
First,
have to
find the
discuss.
closed loop transfer functions.
Correct. Then
Then find the characteristic equation. I mean, poles of characteristic equation in relation to K.
correct.
And then we'll get it. So, and in order to be sustained oscillations, the damping ratio should be 1, but this is not a second order. Right?
Damping ratio should be no. See,
1.
for you have gone till now. You're correct. You have to find out the characteristic equation, right? Unity
Yeah.
feedback system. Fine. Then,
Then find the poles in relation to K.
okay, what will poles tell us about? We have to find
Stability,
out
right?
stability. Okay, where is
Yeah.
a location of poles? But you have to find out the stability as a function of K, right?
Yeah.
So, how will poles help you in determining this thing?
Yeah, the real part should be negative. The real part of the pole should be negative.
That is correct. That is by the location of the poles, you can tell whether the system is going to be stable or not. Fine. But you have to find
Yeah.
out the relationship between K and the stability. So, how will you do that?
Should we plot root flow?
No,
Yes.
no, no, not necessary. It's very simple. By forming the Routh array, we can simply find out like what will be the values of K for which our system is going to be stable. Do you remember that it is not mentioned
Yeah.
exactly? Okay, that you have to apply the Routh criterion, right? Okay,
Yeah.
so you have to, by looking at the problem, you have to decide that how to proceed and what to apply, because there are many tools by which you can find out, right? So if I see the solution here, what will be the characteristic equation? You were right for the stability part, but then for function of K, you have to find out, you have to form the array, right? So this is equal to 0, unity feedback. So HS is 1, fine. So 1 plus K by S plus 2, S plus 4, then S square plus 6S plus 25. Fine. So see what you will get on solving this. Yeah.
No, so if they don't mention anything, we take it as negative unity feedback.
Yeah.
Okay.
I've told you in the beginning, a unity feedback control system is having a open loop transfer
No, no, no.
function.
My
Okay.
doubt is it negative feedback or positive feedback?
Yeah.
So,
Yes. Yes. So what you're getting here?
S cube plus 31 S cube.
S cube. It will be S to the power 4 here. You
Yeah,
can
S power
see.
4. Yeah, yeah, S
Uh-huh.
power 4.
So what you're getting, S to the power 4 plus, you have to expand it, right?
Yeah,
Yes, do it and tell me what you're
12
getting.
S cube
12 S cube, correct? Plus,
plus 33 S class. No,
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 it is
not
not
33.
30.
So it's
No,
37.
it's not 33. It's
uh,
69 S square, right?
yeah,
Plus 198 S plus 200 plus K, correct? Getting it?
yeah,
Yes, ma'am.
Yes. Now I can form the array and put in the values here 1, then 69, then 200 plus K for the first row. Here comes 12, 198 and 0. Okay. So evaluate this. What will be the entries in this row? And tell me.
Fifty 52.5.
Correct. 52.5. Right. Then This is 12 into 69 minus 1 into 198 divided by 12. That will give you 52.5. Okay. And the second entry will be 12
Here
into
it's
200
200 plus k.
plus k minus 1 into 0 by 12.
By 12.
So it will be 200 plus k. Right? Okay. Then
Okay.
what we'll get here? This is 52.5 into 198 divided by 52.5, that is 198 minus 12 into 200 plus k divided by 52.5, right? And here it will be this into 0, and here no entry is 0, so 0, right? And what will be the last row here? This multiplied by this, right?
200 by this.
Yeah, divided by this. So our last entry will be 200 plus k. Now the system will be stable when all the entries of this first column or all the values of the first column, they are greater than 0. Correct? For the system to be stable. So what we'll get from here? I can write down from here that 200 plus k, that should be greater than 0. Fine. Which gives me that k should be greater than minus 200, right? And 198 minus 12 into 200 plus k divided by 52.5, that should be greater than 0, right? Solve this and tell me what will be the value of k from this expression. How much you're getting?
666.525.
666 point, correct. K is less than, right? 666.254. 2.254, right?
Yes.
0.25.
I get, yeah, till
Okay.
0.25.
Okay. Okay, fine. Fine. So see, I've got the values of k, and I can say that my system is going to be stable when the k is in this range. Okay. That is, k should be greater than minus 200. Okay. And less than this. So can I write down this both equations like minus 200 is less than k and k is less than this value? Is it clear, everyone? Okay.
Ma'am,
Yes.
so here we can have negative k also.
Obviously, we have obtained here like for this, because if this is negative, so this will become 0, right? And there is no sign change here, and my system is going to be stable. Fine.
Yes.
Okay.
So
So
only in
I'm
root locus we take k grade from 0.
from
Here we
0.
can have negative k also.
Yes. Yes. Okay.
Yes.
Now see, I'm giving you one more question here, right? You see, you have to, for the same problem, subpart is you have to determine k which will cause sustained oscillations in the closed loop system. Okay. And also find the corresponding frequencies. Can you do it now? If I would have given you this earlier, so you could have make it out that this has to be solved by using Raut-Hare, right?
Yeah.
Okay. So you know that for the sustained oscillations, we have to like see for the values of k. Now this k is the highest value is 666.25, and the oscillation will occur at this value of k, right? So can I form an auxiliary equation above the row from where I got this value of k? Do you remember? Which we have discussed earlier, that as k is equal to 666.25 and it is the highest value, the oscillations will occur at this value of k, right? Fine. So what will be auxiliary equation? Tell me. The auxiliary equation will be from this row, that is 52.5 s square plus 200 plus k equals to 0. Correct? And I have the value of k as 666.25. So for that value of k, can I find out what will be the frequency of oscillation? Yes or no? So I can write
Yes.
it here as 52.5 s square 200, sorry, plus 200 plus 666.25 equals to 0. And now in place of s, I'm writing this as 52.5 j omega square plus how much this will be, 866.25 equals to 0. So find out the value of omega, how much it comes out to be.
4.06.
4 point, after taking the square root, j omega. Yes. J omega comes out to be
4.06.
correct. Absolutely correct. This is plus minus 4.06. Okay. So the frequency of oscillations is 4.06 radians per second. Fine.
Ma'am, how
Okay.
did we know that for the maximum value of k only the oscillation will occur?
This one, this value, how we have selected the, see,
Yes.
this value we have obtained from which row? We have obtained it from this row, right? So the auxiliary equation is formed from the row just above the row from where we have evaluated the value of k, right? So this, if we form the equation, this is 52.5 s square, and the next term will be s to the power 0, right? This is, here you have even power, right? So the powers of s should be even. So after s square, it comes out to be s to the power 0. Is it clear how to get it? Auxiliary equation.
Yes.
One small done.
Which one?
See, actually, usually a system will have sustained oscillations when it's marginally stable, right?
Sustained oscillations.
When it is marginally stable, like when the
Correct.
poles are on the
Correct.
imaginary
That's
axis. So that's the
why we
reason we
have
have taken the extreme
correct.
case.
You are
Yeah.
correct. That's why we have taken the value of k is equal to, right? And for when we have
Yeah.
the value of k is equal to 666.25, the system is going to be marginally stable. Okay. And for the system to be stable, the value should be less than this, right?
Yes, ma'am. So
Okay.
that's the reason we take the extreme value of this.
Yes. Fine. So shall we move to the next question?
Ma'am,
Yes.
for which case we do the derivation in this?
Which derivation, Muthu?
I think in the coefficients of the
Like
auxiliary.
there are two special
Your
cases
voice
in
is
right
not
values.
clear, so please be a bit
Oh.
louder. Yes.
Yes, ma'am. In the auxiliary
Hmm?
expression, we
Hmm?
for one case we take the derivative, right? For
When all the values of a row are equal to 0.
okay, okay.
Okay, that we have already
Yes, ma'am.
discussed. You can just go to the previous video and then you can see. Okay, we have discussed that.
Yes, ma'am. Yeah, yes, ma'am.
Okay, so let us do a problem on state space equations. Okay, we are good up till here, right? So
Yes, ma'am.
our system is characterized by the following state space equations, right? I'm giving the state space equations as x1 dot x2 dot equals -3 1 -2 0 x1 x2 plus 0 1 u, and y is 1 0 x1 x2. The first part is you find out the transfer function of the system. Your exam is scheduled on this Sunday?
Yes,
Yes.
ma'am.
Okay, the live sessions are till, I guess, on till Wednesday.
I think only that Wednesday is there.
Yeah, yeah.
Right.
Okay. So if you wish, we can have one more session tomorrow. Like now, as someone has mentioned, like they want that how we can change the canonical forms and all. Na? You can just tell me your doubts. We can have a session tomorrow. And I can tell you the time. Or you can just post in the G space. Yes?
Yes, ma'am. One more session on problem solving. If we can have tomorrow, it will be.
Yeah, yeah, we can have. You can just post your doubts on the G space. Okay. Or you can just tell at the end of the session. We can discuss that. Fine.
Yes, ma'am.
Okay. So for this transfer function of the system, now if I compare this system with my standard system, what can I write down? What is my matrix A? That is -3, 1, -2, 0, right? Then matrix B is 0, 1, C is 1, 0, and what about D? That is 0, right? So how to find out the transfer function? What is the expression?
Si minus A.
Yes, Ys by Us or Cs by Rs, whatever notations we are taking, that is C into Si minus A inverse into B plus D, right? This is how you find out your transfer function, correct? Where Si minus A inverse is adjoint of Si minus A by determinant of this, right? So how to find out adjoint of Si minus A? That we have discussed earlier, yes? First, you have to find out the cofactor matrix Then you have to find out its transfer function. Sorry, transpose of that. That will give you the adjoint, right? So what is Si minus A here?
S plus 3 minus 1, 2.
Yes. You have calculated that. Minus A. A is how much? A is minus 3, 1, minus 2, 0, right? So this comes out to be how much? S plus 3, then minus 1, 2, and this is your S, right? What is a cofactor matrix? Since this is a 2 cross 2 matrix, you can easily find it out, right? But if it is a 3 by 3 matrix, you should know. But this is simple. You can directly write down. What is the adjoint coming out to be here? Anyone calculated that?
Yes.
Okay.
1.
A cofactor
So
matrix is what? Can you tell me quickly?
yes.
S minus 2,
S
1.
minus 2.
S minus 2, 1, S plus 3, right? And adjoint will be transpose of this, right? So it will be S1 minus 2, S plus 3. All of you know how to find out the cofactor matrix and then transpose. Everyone knows this, right?
Yes.
Yes.
Okay. So Si minus A inverse is S1 minus 2, S plus 3 divided by the determinant. How much it comes out to be? S square plus
3s plus
3s
2.
plus 2, right? So now the transfer function can be written as matrix C, that is 1, 0, multiplied by Si minus A inverse, that is S1 minus 2, S plus 3, right? Divided by S square plus 3s plus 2 multiplied by 0, 1, right? Okay. So you know multiplication of the matrices. Yes or no?
Yes, ma'am.
Okay.
Only the denominator.
So how much it comes out to be here?
Just the denominator.
S into 0, this is 1, right? No, we are multiplying these two matrices, right? First. So this is S into 0, 0, plus 1 into 1, 1, minus 2 into 0, 0, plus S plus 3, that will come out to be S plus 3, right? We have a, yeah, you were telling the answer, right? So this is 1 into
Yes.
1, 1, plus 0 into S plus 3, that is 1 by S square plus 3S plus 2, right? So this is the transfer function of the given system that is characterized by the state space equations, right? So can you find out the controllability and observability of the system, whether they are controllable, whether this system is controllable or not? Yes. What is the controllability matrix?
B A square. So
Hmm?
A minus BK.
That is correct. B,
Oh,
AB, right?
Yeah,
okay, yeah.
Fine.
yeah.
So find out what is B. B is given to us. That is 0, 1. And what is matrix AB? B is 0, 1. AB find out -3, 1, -2, 0. And this is 0, 1. So how much it comes out to be?
1 0.
1 0.
1, 0. Right. Okay. So now the controllability matrix that can be written as 0, 1, 1, 0. Is it correct?
Yes, sir.
Fine. So tell me what is the rank of this matrix?
2.
2.
Correct. Rank is 2. So what is your comment? Whether the system is controllable or not?
Yes.
Yes, system is controllable. Fine. So now if I want to see the observability matrix, what it will be? That I can write down as, yes, CCA,
C.
right? Fine. What is C? C is 1, 0. So find out CA. That is 1, 0. And this is -3, 1, -2, 0. How much it comes out to be?
-3 1
-3,
1.
right? So this is 1, 0, -3, 1. And what is the rank of this matrix again?
2.
2. So the system is observable, right? Okay.
Yes, ma'am.
So if I ask you to find out the transfer function, comment on the controllability, observability, and then to design the state feedback controller and observer, can you do it? As we have seen in the assignments. Could you solve that problem? Yes?
Yes.
Okay. You just go through it and let me know if you have any doubt there. Okay. Let us do one more problem on like how to linearize. Okay. If you have been given a non-linear system, how to compute the equilibrium points and how to linearize the system. Okay. Let us do a problem based on that. A nonlinear system is given as d square x by dt square plus a 1 plus x square dx by dt plus x is equal to 0. What you have to do here is you have to compute the equilibrium points and you have to comment on the stability of those points. Okay. Right? Do you get the question?
Yes, ma'am.
Okay, fine. So tell me how to approach this then.
Just write the state equations.
Hmm? Have you seen that how we can use Jacobian linearization in the videos? I'm giving you a hint here that we have to use the Jacobian linearization for solving this problem. Now tell me how to do this. Yes?
We can first find the equilibrium point.
You write the state equations first.
Okay. Okay, first we have to write down the state equations. Then we have to find out the equilibrium points. Okay, let us start. So let x1 is equal to x, right? And d, and I can say x2 equals to d by dt of x, right? So can I write down now my system here becomes dx1 by dt, that can be written as x2. Please see here, as we have taken x2 as d by dt of x. Now if I'm taking the derivative of x1, can I write down this as x2? Because this is what? Dx by dt only. Yes? Fine.
Yes, ma'am.
And what is dx2 by dt? What is dx2 by dt? That is
X2 dot.
Correct. D square.
d by dt of x, right? That is d square x by dt square. Yes or no?
Yes.
Okay. So if I see this equation, from this equation, can I write down dx2 by dt, that is d square x by dt square, as minus a 1 plus x square, and for dx by dt I'm writing this as x2, right? And this,
Section.
yeah, this is x as x1, correct? I'm doing all this exercise to find out what? My equilibrium points, right? For equilibrium points, what I'll do? Yes,
Equate x1
for
dot and x2 dot to 0.
correct. I'll set dx d by dt of x1 is equal to 0 and d by dt of x2 is equal to 0. Now tell me, if I set both the values as 0, what will my equilibrium point be? Just have a look and tell me.
X equals 0.
It's equal to 0. Okay. So equilibrium point, all of you got this? Equilibrium point is x1, x2. That is equal to 0, 0. Right? If I'm setting this as 0, this as 0. Okay. So x2 is 0 from here. Fine. Once x2 is 0, I put this as 0. x2 is 0. This is 0. Right? So x1 will also come out to be 0. Fine. From here, this becomes 0. And from here, x1 becomes 0. Fine. So this is my equilibrium point. Now what is next? What is the next step?
Jacobian.
Yeah, I have to evaluate the Jacobian matrix. Okay. So Jacobian matrix is once evaluated, then we will use that matrix to compute the eigenvalues and study the local stability near the equilibrium using linearization. Fine. So that's why we are evaluating this Jacobian matrix. So how to evaluate that? You know that vector function is f x1 function of x1 x2. That is your f1 is equal to x1 and f2 is equal to how much? Minus a 1 plus x1 square x2 minus x1. We have written this earlier, right? This. Okay. This is our, right, dx2 by dt, and this is our dx1 by dt. Fine.
Yes, ma'am.
Okay. So now we have to form the Jacobian matrix. So what we have to do? We have to find out the partial derivative of f1. That is what we have taken. That we have taken as x1, right? So tell me what it will be. Del by del x1 of f1, that is equal to
1.
I'm sorry, there is a correction here. F1 will be here. This is x2, right? This is not x1. This is x2. See here, right? dx1 by dt, this is x2. So this comes out to be, this is x2. I'm sorry, make a correction here. So this comes out to be 0 now. And what will be del by del x2 of f1 now? That will be 1, right? Similarly, if now I find out the partial derivative of f2, that is minus a 1 plus x1 square x2 minus x1, what it will be? Del f del of del x1 f2, that is how much? Minus a, that is 2x1, right, into x2 minus 1, and del by del x2 of f2, how much it will be? Minus a 1 plus x1 square. Is it correct? Are you getting the same?
Yes.
Okay, fine. So now the equilibrium points which we have obtained as 0, 0, what will be these derivatives? Let us find out at equilibrium point. X1, x2, that is equal to 0, 0. What will, this is fine, right? Here we have to see del f2 by del x1. How much it will come out to be? Minus 1. Fine. And del f2 by del x2, how much it will be? This will come out
Minus
to
E.
be minus
A.
a. Fine. Right? So now if I am forming my Jacobian matrix, what it will be?
Zero, 1,
0, 1.
-1, -a.
Fine. -1, -a. Correct. So what is the next step then? Now we have this Jacobian matrix. Okay. And we have to find out now the eigenvalues, right? So what will be our next step? We have to form the characteristic polynomial. Okay. So for finding out the characteristic polynomial, we have to find out the determinant of, yes, j minus lambda I, right? Do you remember? So this is 0, 1, -1, -a, and minus lambda I, that will be lambda 0, 0 lambda, right? So how much it will come out to be? Minus lambda 1, -1, -a, minus lambda. Find out its determinant, how much you're getting it. That will be lambda square plus a lambda plus 1. Correct? And the characteristic polynomial is lambda square plus a lambda plus 1 is equal to 0. Right? So what will be the eigenvalues? Can we find out from here? Eigenvalues are, yes, this is a quadratic equation. What will be the values here? That can be written as minus a plus minus b square minus 4ac, that is a square minus 4
4.
divided by 2a, right? If you compare it with the standard quadratic equation of ax square plus bx plus c, right? Okay. So
Yes, ma'am.
we have three conditions here. The first condition is if a square minus 4, that is greater than 0, then we have real and distinct eigenvalues, right? Okay.
Yes, ma'am.
So this is real. So the system is going to be stable in this case, right? Because the real part of this lambda, that will be less than 0. If this is greater than 0, right, then this is minus a by 2 plus minus some value, right? Okay. So the real part of lambda is less than 0 in this case. Second is, you can write down here that for this value greater than 0, our,
Ma'am,
yes,
for a square minus 4 less than
Hmm.
0 only, we can say that it is definitely stable.
no, for a square minus 4 less than 0, we are going to have complex conjugate eigenvalues with real part as minus a by 2, right?
Yes.
Yes. See,
Yes, ma'am.
we are having three conditions. Let us see the condition first, then we'll talk about stability. Here, real
Okay.
and equal eigenvalues. Fine. And in the third case, we have a square minus 4 less than 0. You tell me. Complex conjugate eigenvalues with real part as minus a by 2. Is it correct? Now you tell me,
Yes,
out
ma'am.
of these three, where do you expect your system to be stable? Because here the system will be marginally stable. Agree? When this is equal to
Based
0?
on the
Yes?
based based on the value of A, right?
Yes, based on the value of A. Correct. I can say from here, if A is greater than 0, okay, the system will be stable, right? Then only this is going to be negative, and this will have
Yes.
some positive value, and the roots will lie on the eigenvalues will lie on the left hand side of the S plane, right? Yes or no? And
Yes, ma'am.
again, if here A is equal to 0, say A is equal to 0, marginally stable because the roots will be purely imaginary, right? Of course, your stability depends on A. Stability depends on A. And for this part, when A is going to be, forget about 4, okay? A is less than 0. So what does it indicate? Unstable for this value of A. You can just put in the values and you can check, okay? Just random values by trial and error you can see, okay? So I guess this is clear to you how to do the linearization using the Jacobian. Yes?
Ma'am.
Hmm.
So here, the second one and third one, it will always be stable, right? If A is plus.
Second one and third one,
Yes, ma'am.
always stable.
In the
Yeah.
second and third case.
Okay, okay. I'm just giving you a situation, okay? Now I'm telling you A is greater than 0. You tell me, will the system stable or not? Will it be stable or not? A is
Uh,
greater than 0.
Yeah, it will be stable.
It will be stable. Okay. Now next is A less than 0. Comment on the stability.
Yeah, still it will be.
Huh? It will be.
Okay, no,
So if it
no, it
is
won't be stable.
no, it won't be, because this part, this minus A by 2, that is going to be positive, right? And it is going to lie here
Positive.
on the
Yeah.
RHS. How it can be stable, right, Muthu?
No, the second case, A square minus 4 equals
We are
0
talking
and A
about
square
this
minus 4.
determinant. We are talking about the determinant, and then we are seeing with what about what type of eigenvalues we are getting, right? And here we are talking about the values of A for which our system is going to be stable or not, right? Here we are doing the stability analysis. You're just mixing two things out, correct?
So the cases A square minus 4 equals 0, we are not considering that. We are considering A. Is it?
No, I'm telling you for these three cases, what will be the type of eigenvalues, right? And here we are
Okay.
talking about that for which values of A my system is going to be stable, right?
Okay.
Got it? And if A is equal to
Mm,
0, not clear still.
no, if A is 0, I think imaginary axis, right?
Yes, imaginary axis. It will be marginally stable, right?
Yeah, yes.
Okay.
Yes.
Now it is fine with you.
Yeah, ma'am, and when
Huh.
in the case where A is greater than 0,
Huh.
so if it is negative, then
A is greater than 0 means it is going to be like some value of say 1, 2, 3, 4. So this is obviously going to always lie here, right? Minus 1 by 2 or minus 2 by 2, minus 3 by 2, right? Fine.
um, Yeah, I mean, if the root value is large,
Mm-hmm.
then is there
How
a
you
possibility of it?
let us take one value. Take A as 3. Okay. So
Yeah,
this is how
for
much?
A3, I think, yeah, it will only on the negative side.
It will be for all the values greater than 0. You can just do it by trial and error. Okay.
Yes, sir.
So shall we stop here today? And like for tomorrow, you can tell me that at what time it will be comfortable for you guys so we can have